In this segment, we'll be talking about graphing equations, and here's the equation we'll start with. It's a linear equation involving two unknowns. We're going to use the point plotting method here. There are several methods for graphing. Point plotting is a rather fundamental one. It is, however, the one that's used in your graphing calculator, which we'll look at a little bit later. At any rate, the notion of point plotting is related to the idea of solution. Now, the solution to an equation like this is a value of the variable or variables, as we have here, that will cause the statement of equality to be true. If x is 2, for example, and y is 1, then we have a solution pair. If x is 2 and y is 1, then let's see what happens. We would have negative 2 times 2, that's negative 4. Then if y is 1, we have plus 1. Negative 4 plus 1, that's negative 3. Negative 3 is equal to negative 3. Yes, that's true. So this ordered pair makes that statement true, and therefore this is a solution to that equation. The whole idea of point plotting is to find solution points and plot them on a coordinate plane. Now, to find the solution points, we make a table of values like this, a table of x and y values that solve this, and we set up the table like this, and we select at random values for one of the letters, and then we solve for the other one in the equation. Now, an easy way to do that is to take the equation and to solve the equation for one letter or the other. This equation is pretty easy to solve for y. If I add 2x on both sides, I have y equals 2x minus 3. Now I can use this version of the equation to complete my table of values. Let's let x take on values, let's say negative 2, 0, 2, 4. And to complete the table, I simply replace x with these values, solve for y, and away we go. If x is negative 2, we have 2 times negative 2, that's negative 4. Negative 4 with negative 3 is negative 7. If x is 0, this term goes out, so y is negative 3. If x is 2, 2 times 2, 4. 4 minus 3, 1. If x is 4, 2 times 4, 8, minus 3, 5. Now let's plot these points. The point negative 2, negative 7, that's negative 2, down 1, 2, 3, 4, 5, 6, 7. And 0, negative 3, 2, 1, 4, 5, and the graph contains these points. Notice that the points are collinear. That's always true with a linear equation. The graph will be a straight line. The points on the line then are collinear. And because of that, I guess we don't need to plot this many points if we're constructing the graph of a linear equation. We only need really 2 points, but for verification purposes, you might tack on a couple more. As equations become more and more complicated, though, their graphs become more and more curvy, so you have to plot more and more points in order to discover the behavior of the graph. The most important relationship between a graph and its equation is the idea that the graph is truly a picture of the entire solution set for that equation. That is, if we take any point on this graph, it has associated with it coordinates, x, y. And these coordinates, when put back into the equation, will make the equation true. So for every point on the line, we have a solution associated with the equation. That's a very nice kind of relationship that we'll come back to quite often. There are some aspects of graphs that can help us in constructing graphs and in noticing certain characteristics about equations and graphs and the relationships between them. The first idea we'll talk about in that regard is intercepts. Now, intercepts are the places where the graph crosses the x and y axis. X-intercept is the place where the graph crosses the x-axis. Y-intercept is the place where the graph crosses the y-axis. Now, to find x and y intercepts, we can simply, if we have the graph, we simply look at the graph. Now, and we're going to do this both ways. That is, we're going to identify x and y intercepts both algebraically and by just looking at the graph. X-intercept G, it's about right here. You see, the place where it crosses the x-axis. We don't know the exact spot because it's not an integer value, but it's in that neighborhood. The y-intercept is exactly right here. It's at -3. Now, a lot of times we want to use x and y intercepts in the construction of the graph. That is, we want to calculate the x and y intercepts and actually plot them as a couple of points on the graph. Now, let me tell you conceptually how that's accomplished. It should make some sense that suppose we don't know where the graph crosses. Suppose that we eliminate the graph. I'll just take it off here. We don't know where the graph is. We don't know how it behaves in the coordinate plane. It may be really curvy, maybe a straight line as this one is. We don't know anything about it. But we do know this. We know some characteristics about intercepts. That is, we know that for any point on this x-axis, that the coordinates of that point are some value of x, but the y component is 0. And if the crossing happened to be out here, no big deal. The same characteristic exists. We have coordinates. The x component is something. The y component is going to be 0. Now that tips us off as to how we find x-intercepts. We find x-intercepts by letting y take on the value 0 and then solving for x. So up here for the x-intercept, we let y be 0 and solve for x. If we're talking about the equation we just looked at, I'll use the original form of the equation. It's negative 2x plus y equals negative 3. And if we let y be 0, we have negative 2x plus 0 equals negative 3. And now it's fairly easy to solve for x. We divide on both sides by negative 2 to find x to be 3 over 2, which is 1.5. You see, and then we could actually plot that point. Now that's the point, 1.5, 0, so that point was right here. Okay, so the x-intercept is the point 3/2, 0. All right, for the y-intercept, it's the same idea. That is, the concept for finding the y-intercept is very similar. We may not know where the graph crosses the y-axis, but for every point on the y-axis, the prevailing characteristic is that the x-coordinate for all these points would be 0. And we don't know what the y is. That's what we're looking for. But the idea that the x component is always 0 tips us off as to what we do. To find the y-intercept, we let x equal 0 and solve for y. All right, let's do that. We have negative 2x plus y equals negative 3. We let x be 0. We have negative 2 times 0 plus y equals negative 3. This term goes out, so y is negative 3. When x is 0, y is negative 3. So the point 0, negative 3 is on the graph, and that is our y-intercept. Let's go through the process of identifying intercepts using this equation. Now, the equation involves a radical, and as we set up our table of values, we might investigate more than just 2 points because the graph is going to be a curve and not a straight line, so we need a number of points to plot in order to discover the behavior of the graph. Also, we need to realize that in taking square root, we can only take the square root of positive numbers or 0 in the real number system. So we have sort of a limitation then on the domain here on the replacements of x. X can't be any less than negative 4. If it were negative 5, for example, negative 5 plus 4 would be a negative number. So that's out of the realm of possibility here. All right, let's go through the notion of making a table of values, and let's find our intercepts first. If we're looking for an x-intercept, then we would let y be 0 and solve for x. If we're looking for a y-intercept, we would let x be 0 and solve for y. All right, for the y-intercept, for the x-intercept, we let y be 0. What do we have here? We have 0 equals the square root of x plus 4. Now we have to solve this rascal. Well, let's see, squaring on both sides will undo this radical business. When we square over here, we get 0. When we square on the right, we get x plus 4. Subtracting 4 on both sides, we find negative 4 is equal to x. So when y is 0, x is negative 4, our x-intercept. For the y-intercept, let's see, we let x be 0 and we solve for y. If x is 0, we can just see right through this. If x is 0, this goes out, so we have the square root of 4 or 2. Let's plot those. We have negative 4 going to 0, so negative 1, 2, 3, 4 at 0, and then the point 0, 2. Now we need more information about the graph. We've already mentioned that we're not going to let x take on values that are less than negative 4, so that means that we won't have the graph. The graph won't make an appearance in this part of the coordinate plane, but it certainly makes an appearance over here. Now, let's plot points then in this interval, and we want to choose some points that are relatively easy to calculate. That is, we'd like to be able to take the square root of squares. And we don't absolutely have to do that because, after all, we have probably a calculator available to us, so we could approximate some values regardless of whether we're taking the square root of a square or not. But because we're doing this all by hand and we're trying to make life easy for ourselves, let's pick some easy values. Suppose I pick for x, let's say, we've already done 0. How about something like, negative 3? Because if x is negative 3, we have negative 3 plus 4, that's 1. The square root of 1 is 1. And that point is, let's see, negative 3, 1. All right. Good. Now what else? Let's see. I've taken the square root of 4. I've taken the square root of 1. I've taken the square root, okay, I've got another one could be that I'm choosing 5 for x, because 5 and 4 would be none. You see, that's the way you think through that. You want to think about values of x that will cause us to have a square in here. Okay, if x is 5, then we have 5 plus 4, 9, 3. So let's see, 1, 2, 3, 4, 5, 1, 2, 3. All right. Good. And the graph then looks about like this. And I want to go through here. And the graph stops right here. Let's take a moment here and look at the graph of this equation. Actually, we're going to pause and take a look at several graphs here, and we want to look at some of the features of the calculator as well. Notice that we are going to be using the TI-83 Plus graphing calculator to feature on this program. Sometimes we'll also be using the TI-83. Now, if you have a different calculator or a computer software program, feel free to use those. It turns out that all of these instruments have remarkably similar capabilities, and even if the button sequence on your calculator is a little different, if you just do a little pecking around, I'm sure you can find the sequence appropriate for your calculator. Well, we'll be using or looking at this particular shot many, many times on our program. This is the viewing window, and we'll be seeing it all of the time. We'll see the buttons below, so there'll be no confusion when I talk about pressing the window button and then entering a particular menu. However, the buttons below we haven't looked at, and if you're unfamiliar with the calculator, it might be important for us to just have a quick peek at those and survey them just a little bit as an introduction. I'm just going to slide the calculator up a little bit here so that we can see those buttons a little bit better. Now, the buttons that are in this region, these 2 rows along with these 4 buttons, are sometimes called editing features. The most important items are, first of all, these 4 buttons. When I say cursor up, down, left, or right, I'm talking about pressing these buttons. They just kind of move an icon around the screen. The next most important button probably is this one. This is the one that's pressed when we enter a variable into the calculator. It's marked x, t, theta, and n for various kinds of variables in different kinds of modes on the calculator. Now, these 2 buttons allow us to enter areas that are above and to the right or left of the buttons down here. If, for example, we want to press the square root button, well, the square root button isn't a main button on the calculator. It's called a second function. Now, notice it's color coordinated with the yellow up here. So these have a color coordination to them. If we wanted to find the square root of 20, for example, then we would want to access this button, and to do that it would be second and then press this button, and we are entering that item onto the calculator, and then we would enter 20 and then equals. But at any rate, so the second function will allow us to enter all of these items that are to the upper left of the buttons below. In a similar way, the alpha button allows us to enter the letters of the alphabet that appear above and to the right of various buttons down below. The D, for example, is the alpha key associated with this one. So when I say, if I would want us to enter D, I would say press alpha D. You see, and what I mean is press the alpha and the D associated with it below, like this. All right, now I mentioned that these are basically referred to as editing keys. A lot of times these are referred to as advanced function keys. Of course, the clear is not so much of an advanced function, but these certainly are. And we're going to learn about those and other aspects of the calculator on a need-to-know basis. Now, the buttons below this row are could be called just scientific keys, because they are the buttons that are remarkably similar to those that are found on a scientific calculator. Now, I'm just going to try to slide the calculator up a little bit here so that we can see many of these. All right, a number of things are kind of important to us here. First of all, notice that there are two things that look like minus signs here. Now, this is actually the subtraction symbol, and this is the negative of. And this button also corresponds to the sign change button on a scientific calculator. The enter button corresponds to the equal button on a scientific calculator. Now, all of the four functions, the four regular functions, are over here. Notice opening and closing parenthesis. We'll be using those from time to time, and a comma button here that's useful for certain purposes. Now, raising to exponents is accomplished in a couple of ways. If we're simply squaring, we can press this button. For example, 5 squared would be 5, and then press this button and then enter, and we would get 25 on display. Now, so this button will square anything that is on display. All right, now if you are raising to a higher power, you need to use this button. So when I say the exponent button, it is this one. You see, and sometimes this is called the hat key. But if we were squaring 5, it would be 5, and then press this button, and then a 2, and then enter, and that's 5 squared. Now, it's especially useful if we're raising, as I say, to a higher power. 8 cubed, for example, 8 hat 3, enter, that's 8 cubed. Okay, so that's the idea for the buttons that lie down in this region. Let's see, are there any others? I think that's about all that are in this area that we really need to be aware of right at the moment. Let's slide back down and actually enter some kind of equation. Now, you know, I mean, if I'm covering all the bases here, I need to say this, that in order to enter an equation onto the calculator, we need to write it in a particular form. Now, I'm going to just turn the calculator on, and you'll see some items here that I've entered using the alpha buttons, and the spacing was accomplished by using a space button in the alpha menu, and that space button is the alpha key on 0, if you're interested. But at any rate, if we have an equation written like this, in order to enter that equation into the calculator, we have to solve it for y. That is, we have to isolate y on one side of the equation. So to do that, we would add 2x on both sides, and that would give us this equation, and now we can enter it onto the calculator. Let's go ahead and do that. Equations are entered by pressing the y equals button, and then we could enter the 2x, whoops, only 1, 2, and the x, that's the variable key, and then minus 3, and now we're ready to go graph. Now let's just survey some buttons up here. The window button allows us to see the units that are designated for our viewing window. X minimum, -10, X max 10, same idea for the Y's. Now these are just horizontal distances, and these are vertical distances. The X scale I'll talk to you about in just a little bit. The zoom feature allows us to zoom in or out in various ways, and we'll also investigate these in just a little bit. But do notice that we can zoom in on a box that we create. We can zoom in at a point that we designate. We can zoom out from a point that we designate, and so on. The trace feature we'll look at in a little while. Here's the graph of the equation that we just entered. Now, let me show you the trace feature. If I press trace and press the left or right arrow button, then an icon will move along the graph. And the coordinates associated with that icon appear at the bottom of the screen. That's real nice, particularly if we're trying to find something like, oh, let's say the x-intercept. Well, let's see, I've got a, now the x-intercept, you know, the place where the graph crosses the x-axis, has a y coordinate of 0. So we would be looking for a y of 0 as we cursor along. And gee, we can't land on a y of 0 here. And that's really because of the kind of setting that we're on right now. We just can't land on that point. But we can change settings and allow ourselves to land on that particular point. For this graph, it turns out that the value here is a friendly decimal. It's just a little short decimal number. And so we need to just change the one little feature on the calculator. I'll go to Zoom. And I can do a couple of things. I can press either item 4 or item 5, I think, and accomplish this. But I'm sure I can accomplish it by pressing item 4. Item 4 is Z decimal. Now the graph comes up. I'm pressing trace. And I'll trace on over to that point. Ah, you see Y is 0. And now I can read the X as the x-intercept. It is at 1.5. All right, just one of the little features about the calculator. We're going to have more to say about that Z decimal item in just a little bit. All right, now notice that let me go back to the standard settings, the default settings. Now that's item number 6 here, and we can access that item either by cursoring to it and pressing enter, or by simply pressing number 6. So either way, we go back to our original feature. Now, notice that the tick marks here, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to the left of the y-axis. And I have 10 to the right, and I have 10 above and 10 below. Well, that's because of the window settings that we have right here. So we can redesignate that if we want to. Now, let's have a look at the scale situation. Back to the graph. Now, notice that there are 10 tick marks in all directions. If I go back to window and set an X scale of, let's say, 2, and go back to the graph, whoops, go back to the graph, then notice that I have a tick mark at every other X unit, left and right. Now, the X scale on the Y-axis is still at 1. So that's what the X scale is all about. We can change it according to some kind of need a little bit later. Let's enter another equation. Suppose I go back to the y equals menu, and I'll enter the equation that we were just discussing on the board a few moments ago. It's I'm pressing second and then square root, and remember it was the square root of x plus 4. So I'll press variable key, and then plus, and then 4, and then close parenthesis. Whoops, missed the 4. 4. Close parenthesis. There we go. Now, notice that the expression that appears under the radical needs to occur within a parenthesis here. On the TI-83 Plus, the opening of parenthesis is an automatic situation. On other calculators, it may not be. So make sure you have the item in parenthesis. Now I can press graph, and I have both graphs coming up on the screen at the same time. If I want to look at only one of them, I can go back to y equals, and I can deselect one of these graphs by cursoring left, and while the cursor is blinking on top of the equal sign, press enter. Now notice that what it does is it causes the equal sign not to be selected here. So I'm deselecting that equation for graphing. I go back to the graph, and I have the graph of only the one that is selected. So I can select, deselect, select, deselect as I see fit. Now let's go back and take off these equations. I'm pressing clear, cursor down, press clear, and now I just want to enter y equals x and look at its graph. Now we're on default settings, I think. Let me look at the window settings. Yeah, except for the scale. The scale is generally 1. But the graph, notice, is angled at a certain way through the coordinate plane. And this angle is a smaller one than that one. And if this is truly y equals x, then the angle right here should be 45 degrees. And the reason that it's not, the reason that the graph seems to be squunched down a little bit, is that the default settings say for us to have the same distance left and right as we have up and down. You know, the x minimum and maximum are negative 10, 10, and for y, negative 10, 10. So that means a total distance here of 20 and a total distance here of 20. But the window that we're looking at is rectangular. So something sort of has to give here. If we're defining the same distance up and down as left and right, then we can think of what's happening here is that the graph is being squunched down a little bit like this, or the graph is being stretched like this. Either way you look at it, it's not a true square perspective. Now, there is a button on the calculator that will automatically give a square perspective, but it's important that we be able to make the calculation ourselves. Let me show you an example. Suppose I go to the window setting and I set the y minimum at, let's say, negative 4 and the y max at 4. Now, that gives us graphically a total vertical distance here of 8, because this distance is 4, that distance down here is also 4. So total distance of 8. Now clearly we don't have a square perspective. To create that square perspective, we take this distance and multiply it by 1.5. 1.5 times 8 is 12. So we want this total distance to be 12. Okay, let's set that up. Now if we'd like that distance to be 12 and we want half of the distance on this side of the y-axis and the other half over here, then we're going to set our x minimum at negative 6 and our x max at 6. Let's go to the window settings and do that. So negative 6 for the x minimum, 6 for the x max, and here's the graph. Oh, that's nice. There's a square perspective. There's just one other topic I want to return to briefly, and it has to do with friendly settings. Friendly settings are settings on the calculator that will allow us to trace left and right and have relatively simple decimals for coordinates of points. Now here I just press trace, and as I trace over to the right, notice that the values for x and y are not very friendly. They're not very nice little decimals. Now I can accomplish friendly values by going to the zoom menu and pressing Z decimal. That's kind of an automatic way to do things. But we ought to be able to make the calculation ourselves. Now notice when I press trace and tracing to the right, I get rather simple decimals here. Now, we need to be able to make the calculation ourselves because it's not always the case that we want this particular window setting. You see, we might want to make this friendly value setting when we are looking at a graph way over to the right or way over to the left or something like that. Now, the settings that give friendly values like this are related to the number of pixels left and right on the screen. There are 95 of them, and therefore there are 94 steps required to step on all of them. If you're on the first one over here, then you would have to step 1, 2, 3, 4, 5, and so on all the way to 94 in order to step on the 95th pixel. Now, that's related to the calculation of that total horizontal distance for friendly values. Now, let me go back to the window setting, and I said there are 94 steps. Well, suppose I take half of 94. That's 47. And I set this at negative 47, and then this at 47. All right, now I'm not going to change my y distance here, so the graph is going to look pretty skewed, but the graph then looks like this, and on trace, notice what happens. I have integer values for x and y. Now, it's the x that I'm more concerned with here, though for a different graph, the y value might be some kind of decimal value. But it's the x that is an integer because we made those particular window settings. And it turns out that the 94 is a rather magical number. If we take the 94 and take an integer multiple or integer divisor of 94, we will get relatively friendly values. And that's why the negative 4.7 works so well, because we're simply dividing by 10, you see, and we're getting a close-up view and also arriving at friendly settings. And we can do the same thing by just doubling these amounts. If I just take, well, up here, if I just do this, now I'm just going to go times 2, all right, and then I'll cursor down, and it'll automatically make the calculation for me. Now times 2. All right, and now I'll go to the graph, and we don't have a square perspective, but no matter, we're after the friendly settings here. And now I just cursor to the right. Notice, once again, we have friendly settings, and it's because of that idea of that total horizontal distance of 94 or 9.4 and integer multiples or divisors of those. Symmetry is a quality of a graph that causes it to look the same on the left and right or above and below one of the axes. For example, here's an example of symmetry about the y-axis, because the graph here looks the same over here as it does over here. Here's an example of symmetry about the x-axis, because the graph kind of looks the same above and below the x-axis. It's kind of a reflection in the x-axis, then, we can say. And in fact, think about the idea of symmetry like this. It's an interesting way to look at it, and actually it has an algebraic correlation here. Think about the notion of folding. If we're talking about symmetry about the y-axis, think about actually making a fold along the y-axis, and the graph sort of, boom, imprints upon itself. And when we have symmetry about the x-axis, we have the same folding quality. We can fold along the x-axis, and the graph tends to fold onto itself either way. Now, here's a third kind of symmetry, and this is called symmetry about the origin. And the folding quality is really a double folding idea, that if I look at this part of the graph, if I fold over here, then the graph kind of looks like this. And then if I fold down, you see it imprints on itself. So with that double fold idea, I have symmetry about the origin. There's another way to look at symmetry about the origin. Generally, we have the situation where if we just twist this rascal around 180 degrees like this, then we have the graph imprinting upon itself. Well, let's think about how a point on one part of a graph either makes an appearance or fails to make an appearance on another part of the graph if we have certain kinds of symmetry. And I know that sounds a little confusing, but by making such an examination, we're going to get to the point where we can examine for symmetry in an algebraic sense. All right, here's what I'm talking about. Suppose I take an arbitrary point on this part of the graph, and the coordinates of that point are x, y. And I make this fold. I go through that folding process. Well, where does this point end up? Well, it ends up right over here. Now, what are the coordinates of that point? Well, it turns out that, gee, all we did was fold along that y-axis, so the x component just came right over here, and now it's just the negative of that x. You see, so the coordinates here are negative x, y, and the y component stayed the same. Now, this characteristic is true for every single point on the graph. That is, if we take any point over here, it could be this x, y. And therefore, if x and y are on the graph, then also negative x and y are on the graph. And that will become our algebraic test. Let me go through this folding idea with the other kinds of symmetry, and then we'll go to the algebraic form and examine the situation. Now here we have, in a similar way, if we take a point x, y, and we go through that folding business. Now we're folding down this time, and this point then, when we make the fold, will make an appearance right here. And the coordinates of this point then would be, well, let's see, the horizontal distance is the same for both of these points, so it's still x, but the y is the opposite of that y. So it's the negative of, or the opposite of, that y. Now, had I chosen, by the way, I don't want to complicate things too much here, but let's understand that this folding business works in both directions. That is, if I had chosen an xy right here, then I would consider the xy up here, and it would be x and the negative of that y. Now, this is the y that's negative, but if I talk about the negative of, or the opposite of that y, then this becomes a positive value. So it's the same idea. That is, any xy pair, you see, on the graph somewhere, when we make the fold, its partner will be x negative y, or x the opposite of y. All right, now let's talk about the folding here. We've got an xy pair, a point right here. When we make one fold, that point moves to, roughly, let's say right here. And now the coordinates of this point will be negative x, y, but we have another fold to go through. We fold down this way, and that point ends up about right, oh, let's say here. And now, from here to down here, gee, these have the same x component, so it's this, and the y then becomes the opposite of the y up there. So whenever x and y, xy is on the graph, the point opposite of x, opposite of y is also on the graph. All right, let's use these ideas then to test for symmetry algebraically. Here's how that works. We want to test for y-axis symmetry using this equation. Now, it turns out that this equation is symmetric to the y-axis. All right, let's make the test. Now, the test involves this idea that this, if x and y are on the graph, then the negative of x and y are on the graph. And so to make the test algebraically, we just replace x with negative x and y with itself, or just don't make a replacement for y, and see if we get the same equation, or see if we can manipulate to the same equation. So we replace x with negative x, and let's evaluate a little bit. Negative x all squared is simply x squared. You see, and now this equation and this one are identical, and therefore we are determining algebraically that we have y-axis symmetry. Let's test for x-axis symmetry using the same equation. Well, let's see. That was the idea. That was that folding, this x-axis symmetry, folding in the x-axis. That was where the xy, that xy point becomes x negative y. So it is the case that if we have this kind of symmetry, then y can be replaced with negative y, and we'll have an equivalent equation. So replace y with negative y. And do we have an equivalent equation? Can we manipulate to an equivalent equation? Well, if we multiplied through by negative 1, we would have y equals negative x squared plus 3. Are these the same thing? No. Therefore, we don't have x-axis symmetry. All right. In a similar way, we would test for symmetry about the origin like this. We would take the original equation, replace both x and y with their negatives, and see if we have an equivalent equation. Well, let's see. This remains the same. Here we have x squared, then minus 3. Can we make this look like that? No, we can't. If we multiply through by a negative, it still won't look like that. So we don't have symmetry about the origin. So the answer here is no. Now, let me show you how the test works, though, in a situation where it will be successful. It turns out that the graph of this equation is symmetric to the origin. Now, to go through the test, to test for symmetry about the origin, we replace y with negative y and x with negative x. And then we manipulate to see if we can get back to this form. Well, let's see. We have negative y equals, now negative x cubed. Negative x times negative x times negative x. Well, that's just negative x cubed. That's this. Multiply by negative 1 on both sides, and we have y equals x cubed. Oh, happy day. These look exactly alike, and therefore we're determining that, yes, the graph of this equation is symmetric to the origin. One of the things that we'd like to be able to do throughout this course from time to time is be able to recognize a graph or construct a graph just by looking at an equation. It's quite an interesting technique. We have to study the relationship between graphs and equations quite a bit to be able to do that. Now, and also that's quite a difference from using the point plotting method to generate graphs. Well, one very recognizable graph from its equation is the circle. And let's develop the relationship like this. Consider this circle whose center is at 3, 4. Now, if we just count out from the center to the outer edge, we'll have the radius of the circle. It's 1, 2, 3, 4, 5, 6. Okay, so we have a radius of 6. And therefore, this distance is 6. Now, we're going to actually develop the equation related to this circle. And it's not too difficult to sort of conceptualize how we're going to do that, because circles are defined as all the points in a plane that are the same distance from a center point. So we're going to use our distance formula for this purpose. Now consider that this point to the edge of the circle is a general xy value. And now let's begin the process of developing the equation associated with this by just taking our distance formula and putting in information that we know. Now the distance that we're talking about is 6, and it's distance from this point to the edge of the circle. All right, the points on the edge of the circle are kind of general xy pairs, but the point in the center is a specific 3, 4. Now, when we talk about difference in x components here, one of these x components, one of these horizontal distances, is the x associated with the point on the edge of the circle, and the other is the point at the center. So one of these x's is 3, you see, because of the coordinates of this point. All right, so it's x minus 3 squared, and then a general y minus the y component for the center, 4. And so we have this equation. Let's manipulate it a little bit. Squaring on both sides will clear the radical, so we have 6 squared is equal to this. Now, when this equation is used, and when we're trying to recognize a graph from an equation in this situation, a lot of times this information is listed on the left side of the equation. So let's just swap sides. All right, so now we have this. Now, notice that the 3 and the 4 are the coordinates of the center of the circle, and that 6 is the radius of the circle. We can generalize this situation like this. We can say, okay, let's just let letters stand in for 3 and 4. Now, not x and y here. We want some foreign letters like h and k. All right, so I'll let this, the x component for the center be h, and the y component for the center be k. And we'll let r stand in for the 6. And now we have a generalized version of what we have up here, and if we can write an equation, or if we can see it in this form, then we can easily identify the position of the center, the coordinates of the center, and they would be hk, and the radius would be r. All right, now, one thing to notice here that's really important is that h and k are numbers that follow minus signs. That's really important, because if we have a plus sign in here, we have to create a situation where the number follows a minus sign in order to be able to see the coordinates of points, of that center point. Consider a circle whose center is at 2, -1, and whose radius is 4. Let's build the equation associated with this, this information. Now, we start like this. We think, well, let's see, the equation of a circle has the form of x minus h squared plus y minus k squared equals r squared. And then fill in the information that we see. Well, let's see, we see x minus the h and k now, coordinates of the center. So the h is 2 and the k is -1. So x minus 2 squared plus y minus -1 squared equals 4 squared. We would probably clean this up a little bit. X minus 2 squared plus y plus 1 squared equals 16. Now, sometimes the equations come to us like this, and we're asked to give information like that about its graph. And we can certainly see through this. Now, the number that follows a minus sign here is 2. But here we would have to actively think about kind of backtracking here and putting the equation back into this form in order to see the y-coordinate for the center. And similar idea for the radius. A lot of times the amount that's squared is what we're looking for, but the amount that's squared isn't evident here until we rewrite it in a form like this. All right, so that's the idea. Suppose we have this information. Suppose we know that the center is at 3, -2, and a solution point to the equation that we're developing is -1, 1. Well, we would certainly start the same way. We would start with the sort of the format or the template for the equation associated with a circle. Let's talk about solution point just a minute, though, because we're going to come back to that in just a second. A solution point means an xy pair that solves the equation that we are developing. Now, what does that mean graphically? Well, graphically, we know that solution points are points on the graph. So this is nothing more than a point that's on that circle that we're trying to find here, find information about. And actually, we could plot this point, we could plot that point, we could find the distance between these two, we would have the radius of the circle by finding that distance. But I think we can be a little more clever about finding that distance. Let me show you what I mean. We start out with this. Now, we replace within this format the information that we know. We know this 3, -2 is the h and the k. So we have the 3 and the -2 here. We would clean this up as y plus 2 all squared. Okay, now we're at a point where we need r. Now again, we could find r, we could find that radius by just finding the distance between those 2 points, that is, using the distance formula. But there's another clever way to do that. We know that every point on a graph is a solution point. It solves the equation. It makes the equation associated with the graph true. And so this xy pair makes this equation associated with the graph true. So let's use that information. This is just an x and a y value. So let's see, if x is replaced with -1 and y is replaced with 1, we have truth in our equation, and therefore we can solve for r, you see. All right, -1 minus 3, that's -4 squared is 16. 1 plus 2 is 3 squared is 9, is r squared, so 25 is r squared. R then is going to be 5. Now, if r is 5, we can put that information back into this form of our equation, and we've got the equation that we're looking for. And it's complete. I'm erasing this because I'm going to come down here with some more stuff in a second. But we have x minus 3 squared then plus y plus 2 squared is 5 squared. Okay. Now, this equation is an equation which is in standard form. We call it standard form. There are 2 forms to equations that are important to us. One is called standard form, the other is general form. The standard form of an equation is a form which gives us information about the graph of the equation. The general form is an expanded form of the equation. The general form associated with this one would mean, well, let's see, let's square here and go ahead and square there. You see, just expand it out, perform the indicated operations. Now this would end up being x squared minus 6x plus 9, and then y squared plus 4y plus 4 equals 25. And then we could throw all the terms on one side, rearrange a little bit. We could have the terms that are squared written first, kind of like this, and then minus 6x, and then plus 4y, and then the 9 and the 4, that's 13. But if we move the 25 over to the left, we'd get negative 12 equals 0. So here's the general form of the same equation. Now, there must be a way for us to take this general form of the equation and move back into a standard form in order for us to understand aspects of the graph and to see those aspects of the graph. And certainly that's the next thing that we want to do. Certainly we ought to be able to do that, and it's not too difficult. Let's go through the process. Here's the same equation, and I want to work back the other way, and here's how we proceed. We put the terms involving x next to one another. We leave a space, put the terms involving y next to one another, leave a space, put our equal sign, and kick the constant to the other side. We're adding 12 on both sides to get this. All right, here's how we're thinking about the problem. We're thinking, okay, here are our terms involving x. Here are our terms involving y, and there's our constant. Now, what we intend to do is create a situation here where we invent a constant which will allow us to factor into a binomial squared. Now, we're trying to create then a trinomial square. And by the way, this is called, the process is called completing the square. You may recall it from another situation. But to complete the square here, we take half of 6, that's 3, 3 squared is 9, so I'm adding 9 here. But if I add 9 here, to maintain the balance of the equation, I need to go over here and add 9 as well. Now, let me continue this one step further, and then I'll address this situation. But factoring here, we get x minus 3 squared. And then over here, we'll do the same kind of thing. We'll complete the square. We're completing the trinomial square. Half of 4 is 2. 2 squared is 4. Add 4 here. To maintain the balance, we add 4 on the other side. And now factoring, we get y plus 2 squared. And on the right, we get 25 as expected. Now, we can recognize then the aspects of the graph that we're looking for. We're looking for the center. You could see the center at HK. Now remember, H and K have to both follow minus signs. That one doesn't. So we have to think of this as minus negative 2. So our coordinates are 3, negative 2, and we have a radius of 5 as expected.